Okay, good. So now the next question would be, how can we evaluate probabilistic forecasts? So the simplest thing that comes to mind is a simple hit-miss rule. That's also called coverage. It can be used to evaluate a forecasting interval. It is directly interpretable. 80% of forecasts are within the interval, right? So the way it works is let's say this is our time series. This is our forecast interval. And now our actuals are something like this. Okay. So now like this rule would simply say, okay, these here are outside of the interval. These ones here are outside of the interval. These ones here are inside of the interval. And then it just calculates the ratio of how many are inside and outside. And that's your evaluation. Right? So you could say 80% of my forecasts are within the interval. So it's a good first evaluation, but it doesn't tell you the full story. So it doesn't consider the magnitude of the error. It just tells you if you are inside or outside. It doesn't tell you by far how far you are outside, for example. And another big problem is that there are trivial solutions possible by just grossly over and under predicting certain amounts of times, right? So you could imagine something like that. So you say, okay, I want 80% coverage. Okay, so I make my interval kind of here way too narrow, and here I make it super large. And now for sure the actuals here lie outside, here they lie inside. Now I got my 80% coverage. But that's obviously not what we want. Okay, so now something a bit more elaborate is this mean scaled interval score that was used in the M4 competition for evaluation. It also evaluates a prediction interval. And the way that it works, so the formula looks quite complicated, but it's actually not that complicated. So it sums over the size of the intervals and the magnitude of the error for points that lie outside of the interval. And so if this model is optimized, but one important thing is that if your model is optimized with pinball loss as a loss function, it will not necessarily perform well under this MSIS. So basically just to make this a bit more clear, so the MSIS here, it just divides by the same in-sample naive average performance as like Maze and RMSSE do. Okay, and then up here, so the idea is the following. So what we have up here in the numerator, the idea is the following. You have your prediction interval, and now you have your actuals. And now what you want to penalize is you want to penalize if you are outside. You penalize by how much are you outside. Both if you overpredict and underpredict. Okay. And then what you also want to penalize is the width of the interval. So like the larger this interval, the more you want to penalize it, right? Yeah, exactly. So basically, yeah, this term here tells you are outside, your actual is smaller than your lower quantized. So that means you're outside of the interval. So this indicator function is 1. So this penalization term is this one down here. Okay. This means you are outside of the upper interval. So that gives you this penalization term here. And this upper minus lower, that's just the interval width. Okay. Good. Another measure that people are using is this scaled pinball loss. Again, it looks very complicated, but again, you just divide by the same in-sample naive average over the training set as Maze and RMSSE do. And then up here, this is just the pinball loss written in a different way, right, with indicator functions. But yeah, it's just exactly the pinball loss. Okay, and now based on the SPL, we can define the weighted scaled pinball loss. That was actually used in the M5 uncertainty track for evaluation. It combines, for example, each series SPL of 0, 1 and 0, 9 quantiles by taking the average, and then it optionally weighs the SPL by a series-specific weight, right? So basically here, you just say, okay, well, here I say all the quantiles I want for a particular series. So for example, 0, 1, 0, 9, and 0, 5. And here now you just sum the SPL over those. And then here you sum over the series. Each series gets a weight that gets multiplied with this average SPL per series. Yeah, so K is the number of quantiles. If you don't want this weighting, you just set the weights to 1 divided by n for all time series so that you get this equal weighting. And yeah, so it's an error measure, so lower WSPL indicates a more precise forecast. Okay, so so far we have evaluated intervals, but there are measures that can evaluate full forecast distributions. I've put here some references of where these things are discussed and introduced and motivated in a very good way. So the most common measure in this space is the continuous ranked probability score, CRPS. And the idea is that it integrates over all the quantiles, right? So that's this integration here. And it's actually a generalization of the MAE to the probabilistic case. So basically, you say if my so f of x is your predicted CDF, and so if this and here basically you subtract this indicator function and then you square. So you see this integration, you need the full CDF to be able to compute CRPS, right? So that's why if you do things like you assume you have a measure like a model like DeepAR and GBoost, like GBM-LSS, they give you a full distribution, so you can use CRPS for the evaluation. But if you run a quantile regression that gives you just one quantile, then you cannot use CRPS. Yeah, and there are still more measures like the logarithmic score, the energy score, the variogram score that I don't really want to go into. There is also for multivariate forecasting. There's this paper here from Seal 2019 that discusses many of these measures. Okay, with that, we leave it there for the probabilistic forecasting. Thank you.